I welcome all of you to the class. In today's class, we'll be talking about the graphical representation of the failure theories. The topic is very important. The title of the topic is the graphical representation of the failure theories. Graphical representation of the failure theories. Okay. So what do the failure theories graphically represent? So first theory that we'll be taking up is the maximum principal stress theory. Maximum principal stress theory. So let's first of all understand what does this theory graphically represent. And the overall representation of this theory is very important for us. So we know from the we know from the maximum stress theory, maximum principal stress theory, that none of the principal stresses, sigma 1, should be equal to sigma y, or sigma 2 equal sigma y. If we are in a two-dimensional space, then essentially we are assuming that sigma 3 does not exist, that is, it's equal to 0. So this condition, if happens in a machine element under the biaxial state of stress, then essentially the failure happens. Or in case of the single state of stress, uniaxial state of stress, if sigma becomes equal to sigma y, then the failure happens. Fine. Now let's take the coordinate system. Let's try it. This is our sigma 1 axis. This is sigma 2 axis. So let's say this is sigma 2 and this is sigma 1 axis. Fine. So none, sigma 1 should not become equal to sigma 2. So that is here. Let's sigma 1 should not become equal to sigma y. Let's suppose this is sigma y. Sigma 1 can attain all the values which are below sigma y. Same is the case with sigma 2. Sigma 2 can attain all the values, but those values should be below sigma y. Okay. So if we draw, we can say that if we enclose it in a region like this, let's enclose it in a region, and let's say this is sigma y. This point is our sigma y, this point sigma y. Then if you look at this first quadrant, quadrant 1, in this quadrant, all the points, the state of stress in a two-dimensional state should be within this square. Okay, should be within this quadrant. Okay, because if it's above this quadrant, for example here, then the value of sigma 1 and sigma 2 both are exceeding. Okay, so the values are more than the yield stress. Look at this point. This point is above sigma y, this point is above sigma y. In fact, this point as well, if you have a point over here, this point is having sigma 1 greater than sigma y, but its sigma 2 is still less than sigma y. Still this point is outside this quadrant, therefore this point represents the point of failure. Machine element should not have this state of stress, it will fail. So the stress distribution, that is sigma 1 and sigma 2s, should always lie within this first quadrant when sigma 1 sigma 2 both are positive. So let's write here, when sigma 1, this coordinate of this pointer, it is positive sigma 1 and sigma 2. Fine. So when both the points are positive, when sigma 1 sigma 2 is positive, then this region, the state of stress for two-dimensional states, should be within this region. That's very important. Fine. Now if both are negative, that is, if sigma 1 is negative, compressive sigma 2 is negative, still this represents, this point over here represents minus sigma y, and this point represents minus sigma y. The state of stress in case of compression should also be such that neither sigma 1 minus sigma 1, neither sigma 2 minus sigma 2 should be exceeding the value of sigma y. That is, in compression as well, the value of the compressive principal stresses should not exceed the value of the yield stress during the compression. Okay, if we enclose this region, it will be like this. We enclose it, it will be enclosed like this. The enclosed region will again be a square region. Fine. That is, if you look at this region, fine, this is the region where all the points, if the stress distribution lies anywhere in this square, in this quadrant, then the machine element will be safe. The stress distribution should not be outside this region for compression. Okay, so the coordinates of this point are sigma 1 comma minus sigma 2, and both these values should be less than the value of sigma 1. Now if you come to the region 2, one is sigma 2 happens to be tensile, sigma 1 happens to be compressive. Neither sigma 1 nor the sigma 2 should exceed the value of sigma y again. So if you enclose this region again, it will be essentially like this. Okay, so it will be like this. So here it is minus sigma 1 and positive sigma 2. Fine. And all the points, the tensile, if the stress distribution is, one of the stress is positive, another stress is negative, then still the points, the stress distribution should be well within this quadrant. And same will happen over here. Let's join these points. We join these points. The coordinates of this point are sigma 1 minus sigma 2. Okay, so this entire region within this square represents what's known as the maximum principal stress theory. That is, whenever your machine element happens to be under the two-directional state of stress, biaxial state of stress, or the plane stress distribution, the values of sigma 1 and sigma 2 should be such that they should lie well within this square. Okay, so if they lie outside the square, the points are represent the points of failure. So that machine element is going to fail. So this is the first graphical representation of the maximum principal stress theory. It happens to be in the form of square. Now let's go to the next theory, that is the maximum shear stress theory. Let's see what it graphically represents. So the next theory is maximum shear stress theory. So what does the maximum shear stress theory represent? Let's first of all see the graphical representation of this maximum shear stress theory. The maximum shear stress theory says sigma 1 minus sigma 2 equal sigma yield. If this condition is met, then the machine element fails. Right? Now we assume that there is a two-dimensional state of stress such that sigma 3 is equal to 0. There is no state of stress along the z-axis. There's a plane stress. We are in a two-dimensional plane. Fine. So if this condition is met by a machine element, if this stress distribution is attained, then the machine element is going to fail. Fine. Now this theory states that the maximum difference in the stresses, that is sigma 1 minus sigma 2, or sigma 1 minus sigma 3, or sigma 2 minus sigma 3, the maximum stress distribution, the maximum difference between the stresses should not be equal to sigma y. Fine. Now we are assuming one of the stresses to be 0, sigma 3 is 0. So the maximum difference is sigma 1 minus sigma 3, where our sigma 3 is equal to 0. This can also be the case. Second is sigma 2 minus sigma 3 equal to 0. This is also the difference between the principal stresses, where our sigma 3 is also equal to 0. So we have to take care of these points as well. Fine. We also know that in case of compression, minus sigma y1 minus sigma 3 should not be equal to 0 as well. And minus sigma 2 minus sigma 3 in case of compression should not be equal to 0 as well. So we have to take care of all these points. That is that sigma 1 minus sigma 2 is equal to sigma y. That is the maximum difference between the principal stresses. If becomes equal to the yield stress, then the machine element happens to fail. See, what we will do, let's plot them over a region. Let's see how we can represent the formula graphically. The just a minute. Let me draw it perfectly. Undo this. Yes. So look at the first point. The first point is this is our sigma y, this point. This is plus sigma y. The point below is minus sigma y. This point is plus sigma y, yield points. This point is minus sigma y. This is our sigma 1 axis, and this is our sigma 2 axis. Okay. Now look at the first line. Look into the first line. The first line says, if we happen to draw a line like this, first line, this line represents sigma 2. This time represents sigma 2 equal to sigma y. That is, our sigma 2 is equal, that is sigma 2 minus sigma 3 should not become equal to sigma y. Okay, our sigma 3 is equal to 0. Therefore, sigma 2 is equal to sigma y. That is represented by this straight line. So we'll write sigma 2 is equal to sigma y. And on this line, we are assuming that our sigma 3 is equal to 0. Fine. Now look at this line. Our sigma 3 is already equal to 0. So sigma 1, if becomes equal to sigma y, the failure happens. That will be represented by a line like this. That will be represented by a line like this. So this line represents for us, this line represents sigma 1 equal to sigma y, where our sigma 3 equal to 0. So if you look at this region represents our two conditions, sigma 1 minus sigma 3 equal to sigma y, sigma 2 minus sigma 3 equal to sigma y. So for the stress distribution where both sigma 1 and sigma 2 happen to be positive, where sigma 1, sigma 2 happen to be positive, then this region represents the region where the stress distribution should lie so that the failure does not occur. That's one. Number two is, if both the stresses are negative, if sigma 1 and sigma 2 both are negative, so we will be having minus sigma 1 and minus sigma 3 should not become equal to sigma y. Sigma 3 is already equal to 0. That is, sigma 1 should not become equal to negative sigma y. Similarly, sigma 2 should not become equal to minus sigma y. So that will be represented by the lines like this. So that is represented by this region. So for compression, it will be represented by this region. So this is the region for which we can write this region minus sigma 1 is equal to sigma y, where our sigma 3 equal to 0. And for this line, minus sigma 2 is equal to sigma y, where our sigma 3 is equal to 0. So this point is having coordinates minus sigma 1, minus sigma 2. Okay. And this point will be having coordinates sigma 1, comma sigma 2. Okay. So this region, this quadrant represents the region where if the state of stress is positive or negative respectively, then the stress distribution should lie well within these quadrants. Fine. Now come to this, sigma 1 minus sigma 2 equal to sigma y. Okay. So when we say sigma 1 minus sigma 2 equal to sigma y, we can have two conditions here. The first condition is sigma 1 is greater than sigma 2. If sigma 1 is greater than sigma 2, fine, then we can write minus sigma 2 is equal minus sigma 1 and minus sigma 1. Sorry, no, not minus, sorry. Sigma y minus sigma 1, fine. Or we can write sigma 2 is equal sigma 1 minus sigma y. Now look into this equation. We have to plot this equation. So when sigma 1 is equal to 0, when sigma 1 is equal to 0, sigma 2 is equal to minus sigma y. So sigma 2 is equal to minus sigma y here, and on this line our sigma 1 is also equal to 0. So this is one point. On this point, the point which I am highlighting here is the point on which the value of sigma 1 is 0 and sigma 2 is equal to minus sigma y. Now say sigma 2 is equal to 0. When sigma 2 is equal to 0, then sigma 1 is equal to sigma y. On this line, sigma 2 is 0 and sigma 1 is equal to sigma y is here. So if we join all these points, because this is represented in the form of a straight line, we'll get a line like this. Fine. Similarly, our case 2 over here is when sigma 1 is greater than sigma, when sigma 1 is less than sigma. Fine. So if we plot the points, the case 2 is when sigma 2 is greater than sigma 1. Okay, so at that time sigma 2 is greater than, so we can have this entire equation will be negative. We will write for this case we'll be having the equation that we'll be having is equal sigma 2 is greater than sigma 2. This entire term, or I can write it like this, let me clean it. We'll be having this term will be negative, that is sigma 1 minus sigma 2 or plus sigma 2, because this sigma 2 is greater than sigma 1. So let me redraw this. Minus sigma 2 is equal to minus sigma y. The reason for writing it like this is because sigma 2 is greater than sigma 1. This answer will be minus. So I'm taking that minus on the right side. Now do it again. If sigma 2 is equal to 0, when sigma 2 is equal to 0, then sigma 1 is equal to minus sigma y. So that point is over here. This is the point over which sigma 2 is 0 and sigma 1 is equal to minus sigma y. One point is here. Now assume when sigma 1 is equal to 0, when sigma 1 is equal to 0, sigma 2 is equal to sigma y. The point is over here. Join these 2 points. So as we join these 2 points, we get a hexagon like this. It's called Trusca's hexagon. Fine. So this is the hexagon. This entire hexagon represents what's known as the maximum shear stress theory. Fine. So the maximum shear stress theory is represented in the form of the hexagon. Now let's go to the theory number 3. The third theory is what's known as the maximum principal strain theory. The maximum principal strain theory says maximum principal theory. The maximum principal strain theory statement is sigma 1 minus Poisson's ratio times sigma 2 should not become equal plus or minus sigma y. If this happens, then the failure happens. This is quite indicative. I mean to say that sigma 1 minus nu sigma 2 is equal to sigma y. Okay, so if you look on the left hand side, sigma 1 represents stress along direction 1. Nu sigma 2 also represents stress along direction 1. Fine. Should not become equal, positive or plus or minus in tensile condition or in compressive condition, should not become equal to the yield. Fine. So we'll write this is stresses along direction 1. Stresses along direction 1. Similarly, we will be having sigma 2 minus nu sigma 1 should not become equal plus or minus sigma 1. This represents stresses along direction 2. Fine. If this is a two-dimensional state of stress, then sigma 3, all the components in direction 3 are assumed to be 0. Now let's plot these conditions. So you are having 4 equations, 2 here, 2 here. So if we went on to plot these equations, let me, if we plot, if we plot these equations, then first of all, we have sigma 1 minus nu sigma 2. Let's take this. Sigma 1 minus nu sigma 2 is equal plus sigma y. Fine. This is an equation of a line. Okay. So when sigma 2 is equal to 0, when sigma 2 is equal to 0, then sigma 1 becomes equal to sigma y. So the point is somewhere here. This is the point. This is sigma y. This is sigma 1 axis. And this is sigma 2 axis. And when our sigma 1 is equal to 0, then our sigma 2 becomes equal minus sigma y divided by Poisson's ratio. Since Poisson's ratio is less than 1, therefore this will be greater than sigma y minus sigma y. This ratio, I mean to say, this ratio is less than 0. Oh, sorry, this ratio is less than 1. Fine. This ratio is equal to 0 0.3, 0 0.34, 0 0.32, 0 0.12. So you have denominator less than 1. So when you divide a number by an integer less than 1, so you will get a number which will be greater than sigma y, minus sigma y. So minus sigma y is somewhere here. Let's say this is minus sigma y. So this line will minus sigma y, Poisson's ratio times minus sigma y will be somewhere here. Okay, so we are not, if we draw a line passing through, it will be somewhat like this. Sorry, it will be a line like this. Like this. Fine. So this is the line which is being represented by sigma 1 minus nu sigma 2 is equal to sigma y. Fine. Now let's go to the next case when sigma 1 minus nu sigma 2 is equal to minus sigma y. Okay. The same condition when sigma 2 is equal to 0, sigma 1 equal to minus sigma y. Minus sigma y is somewhere over here. This is minus sigma y. And when sigma 1 is equal to 0, sigma 2, this will be plus. Okay. So it will be greater than plus sigma y. Plus sigma y is somewhere over here. If this is positive sigma y, fine. So sigma y divided by nu will be a point somewhere above this. Okay. So if we draw a line, the line will essentially be like this. One line. Okay. So then take the second condition, third condition rather, that is sigma 2 minus nu sigma 1 is equal plus sigma y. Fine. So when sigma 1 equal to 0, sigma 2 is equal to sigma y. Okay. So sigma 2 is equal to sigma y is over here, this point. And whenever sigma 1 is equal to 0. So this is here. So if you draw this line, the line will essentially be like this. So you have to draw a line passing through the sigma y. It will essentially be like this. Like this. Fine. Now take the second case when sigma 1, sigma 2 minus nu sigma y is equal to minus. So instead of sigma 2 equal to plus, you will get sigma 2 is equal to minus sigma y. So if you draw a line over here, it will be like this. So essentially, what we obtain is it will be essentially somewhat like this. Okay, so this is the region. This is the region. 1, 2, 3, 4. Let me write it like this. This is the region. This is the region that represents the maximum principal strain theory. So in the maximum principal strain theory, as far as our distribution of stress, sigma 1 and sigma 2 lie within this region, entire region, then the machine element is not going to fail. Okay, so this is essentially a parallelogram. You can see it. So as long as it lies within this parallelogram, the machine element will not fail. Now let's move to the next theory. The next theory in hand is the maximum strain energy theory. If you look at the maximum strain energy theory, maximum strain energy theory, the expression for the maximum strain energy theory is sigma 1 square for in case of 2 dimensional plus sigma 2 square minus twice nu Poisson's ratio times sigma 1 into sigma 2. If becomes equal to sigma yield, the machine element fails. If you look at this equation, this is an equation of ellipse. So this is equation of ellipse. This is equation of ellipse with axis at 45 degree to sigma. That is, if we plot this equation, this is an equation of an ellipse, it will essentially be like this. Let me draw the quadrants first. Let's draw the ellipse. So the ellipse, if we plot, it will essentially be like this. To essentially be an ellipse like this. Okay, if we can plot it correctly, an ellipse will be like this. Fine. So this ellipse will be like this, with its axis being at 45 degree. Okay, if the points lie within this region, then by the maximum strain energy, the machine element is not going to fail. The failure will not happen as long as it's within this ellipse. Same is the maximum strain energy theory. That is the distortion energy theory. If you look at the maximum strain energy theory or the distortion energy theory, the expression for the maximum strain energy theory is maximum strain energy theory. Okay, with its expression, its graphical representation is also in the form of an ellipse. Okay, can verify it with the help of the already derived equations. Its representation is also in the form of an ellipse. And if you draw an ellipse, it's essentially like this. The ellipse is like this. This is the ellipse that is being represented by, that represents the maximum strain energy theory. You can draw it neat and clean. I don't think there is an option of drawing an ellipse using the board that I'm using. So you can draw it perfectly. So this represents what's known as, this ellipse represents the maximum strain energy theory. This is minus sigma 1 minus and plus sigma 1 sigma 2. This point is minus sigma 1 plus sigma 2. This is minus sigma 1 minus sigma 2, two quadrants. This is sigma 1 minus sigma 2. So this is the ellipse. So as long as you are within this ellipse, the machine element will not fail. So this is the graphical representation of all these 5 theories of failure. So now we are left with the numerical portion, which hopefully we'll be taking up in the next class.